Hi, and welcome to Math 232, Section 3.4, Special Subspaces. What we're going to get at here, really the sort of crux of this whole thing, is that for each matrix, there are four fundamental subspaces. There's going to be the column space, the row space, the null space, and the null space of the transpose. We're going to identify what those things are and how we figure out what they are. And then we will finish with the Rank-Nullity theorem. That is a rather fundamental theorem of linear algebra. Okay, there's a lot of vocabulary in this lecture, maybe more so than some of the other ones. So make sure at the end of this, if you look back through the lecture notes, that if somebody said to you, what is a kernel or what is a null space or something like that, you would be able to say what it is. You got to know what the meanings of the words are. Okay, so those, in fact, range, null space, kernel, column space, and row space are defined right here at the top of the lecture. So let's get into what these things are and what we can use them for. Okay, so the range, here it is, the range of a linear mapping is defined to be the set, which are basically the possible outputs. So we have we have a domain for our linear transformation that is all of the possible inputs, and then whatever output, the full set of outputs that results from that is the range. Okay, so that we would read this here is the range of L, the linear transformation or linear mapping. The range of L is all the functions, all the outputs of the function L when given the inputs X, where X is in the domain. Okay, so in this case, in the statement, the domain is Rn, and the codomain is Rm because the outputs are in Rm. Now, unless this is an onto linear mapping, we won't be able to reach all of the vectors or all of the outputs in the codomain. So we want to identify that we can only reach some of them. That's what the difference between the range and the codomain is. So the range is a subset. Range is a subset of the codomain. Okay, so we have some sort of a codomain here. We have a domain over here. And we have our transformation, which maps vectors from the domain to vectors in the codomain. And in here, inside the codomain, will be all of the possible outputs. And that's what we call the range. So we're in here like that. And it might be the whole thing, but it might not be. And so there it is. That is the range. Okay, so that's what the difference is between them. Okay, the range is a subset. Is it a subspace? Is the range a subspace? It's a subset, but maybe it isn't a subspace. We need to think about this. And the answer to that question, let me just tell you the answer. Yes, it is. Okay. And the basic reason for that, I'm just going to wave my hands around here. I'm not providing a proof here, but the basic reason for that is because we are dealing with a linear transformation. So linear combinations of the input result in linear combinations of the output. So, and then the fact that all linear combinations of the various outputs are in the range is what allows it to be a subspace. Let me just write that down. So we're going to note that L is linear. And what does that mean? That means L of Cx is equal to C times L of X. Right? So when we have a scalar multiple of our input, we get in our output the scalar multiple of the output of the unscaled input. Okay, this of course means this statement right here allows us to see that when we take C equals to 0, that the 0 vector will map to the 0 vector. Okay, that always happens in subspaces. Okay, and we can also see, because L is linear, that L of Cx plus dy, two inputs. Let me, in fact, why don't I just so there's no confusion between X and Y, let me call this L of Cx1 plus D of X2, like that. So we've got two vectors in the domain, and we apply the linear transformation. We will get CL of x1 plus dl of x2. Okay, so yes, the range is a subspace. So let's look at a specific linear transformation here and identify the domain, the codomain, and then find the range. Okay, the domain and codomain are super easy. You just look, what vectors are we allowed? You can see that the transformation takes 3 inputs. So here the domain is, so would be a 3-component vector. So the domain is R3, and it produces a 2-component vector. So the codomain is R2. Okay, so you should be able to just look and write that down quickly. Okay, meanwhile, the range is a little bit more difficult because we don't know, actually, given all possible inputs into the transformation, will we get all of R2, or will we just get some portion of R2? That's the question. So we have our transformation. I'm just going to write it out in this way. This is not a vector. That is the first component of X, and then the second and third component of X. And I'm going to rewrite that yet again in this way. That is X1 times this vector plus X2 times this vector plus X3 times this vector. Okay, so we see that basically just by rewriting out the transformation in a different way, we see that really that the transformation takes all possible input vectors, and it provides this linear combination. So that means, in fact, I'm looking then at being able to produce all linear combinations of these 3 vectors here. So the range of L is the span of these 3 vectors. Because I'm allowed to choose any, I mean, X1, X2, X3 are real numbers. I'm allowed to choose whichever ones I want on the input. So I then see this, because I'm taking all linear combinations of these 3 vectors, it means that that output there is the span of those vectors there. Okay, now I ask the question that we've been asking before, what subspace is this? It's a span of something. We know it's a subspace. What subspace is this? And this one, I mean, we've got 3 vectors in R2. So we clearly don't even need that many. And then I can look at this and I can quickly see that there's 2 of them in here that are linearly independent. For example, this one and this one are linearly independent. So there's 2 linearly independent vectors in R2. So the span here is R2. This is the span of R2. So, and then of course we would say that this here, 2, 0, 0, 2 forms a basis. A basis for the range of L, and it's also in fact forms a basis for R2 because this subspace is R2. Okay, so we have the idea of domain, codomain, and range. Okay, and let's now look at what we mean by the word null space or kernel. This turns out to be a fairly important concept, and it's basically what input gives you the 0 vector on the output or the 0 answer on the output. So we're looking at a linear mapping, and we're saying we want to identify all the vectors that whose image or who maps to the 0 vector. That's what this statement is saying here. The null space, the null space of my linear transformation is all the input vectors such that the output is 0. We also sometimes call this the kernel. This is a more general word used maybe not even in the context of linear algebra. Okay, for linear transformations, which is us in linear algebra, the null space is a subspace. Okay, so let us just make a couple of hand-waving arguments for that. For the same reason as it was on the previous slide, the 0 vector is in, right? Because we have a linear transformation, and we have this thing, and then we put c equal to 0, and we see that the 0 vector is in. And if I was to choose, for example, x1 in the null space, okay, we know that there's at least one we know there's at least one vector in the null space, the 0 vector. Okay, so now I'm going to pick x1 in the null space of A. And that means because it's in the null space, that when I apply the linear transformation to it, I will get the 0 vector. Now I pick some other vector, which is in the null space. And when I apply the linear transformation to that, I will also get a vector I will also get the 0 vector. Now I imagine taking the linear combinations of these guys. So I take L of Cx1, that's a scalar multiple. And because it's a linear transformation, I have this, and then that one is equal to 0. Okay, so we have that. And then we also have, if I take the linear transformation of the sum of these two, I get the sum of the linear transformations. And that is also equal to 0, because that's 0 plus 0. So I have that scale, I have the 0 vector in the null space. And then when I take scalar multiples, I'm in the null space. And when I take, I add two vectors which are in the null space, I get another vector that's in the null space. So the subspace is closed under linear combination. The null space is closed under linear combination. It is a subspace. Okay, let us now try to find the null space of a linear transformation. It's the same example as on the previous slide. So here we have this linear transformation. What does it do? That's our linear transformation, and we want to ask, when does that equal the 0 vector? For what values of x1, x2, x3 do we get the 0 vector? Or I could also write this like this: 2x1 is equal to 0, or minus 2x2 plus 2x3 is equal to 0. I'm going to put that, this is two equations, three unknowns. I'm going to put that into an augmented matrix. There it is. I'm going to row reduce. This is pretty easy to do. I'm just dividing the first row by 2, and then I am multiplying the second row by -1. Okay, now I've got down to the row reduced echelon form of the matrix, and now I can write out the solution set. And then I see there's 2 leading ones. There is no leading one in the third column. x3 is free. I assign that to be equal to 2, t. x2, now I'm looking at this line right here. x2 is 2x3, and that is 2 times t, because x3 is t. And then I look at this row here, and I see that x1 is 0. So now I have the solution set for all vectors x1, x2, x3, such that L of x will be 0. And that solution set is this guy here, 0, 2, 1. It's a line. So the null space of the linear transformation L is the set of all vectors of this form, such that t is a real number. Okay, and that is a line. The other way of writing this is that this here is a basis for the null space of L. Okay, so we can find the null space. As mentioned at the beginning of the lecture, there are 4 fundamental subspaces, and so now we're going to look at those. So we have a matrix A, and it's got columns. It's got n columns, which are of each of dimension m, and the column space is defined as the subspace spanned by the columns. So all you do is take the columns of the matrix and ask, if I consider this as a list of vectors, n of them, what space is being spanned? That's all. And that basically amounts out to being all linear combinations of the columns of A. Let's just take a look at this as an example. We'll take the matrix A, looking like this: 1, 2, 8, 1, 1, 5, 1, 0, -2. There's a matrix. It is a 3 by 3 matrix. So we're going to, in this case, n is going to be 3 and m is also going to be 3. There are 3 columns. Okay, we're talking about the column space here. So we have the column space, which we write like this. The column space of A is the span of the column vectors of A. There. That is the column space of A. The way that you see that this is all linear combinations of the column space is all linear combinations of the columns. Let's just do this multiplication. 1, 1, 1, 2, 1, 0, 8, 5, minus 2. We're going to multiply that by a generic vector x, and let's see what happens. And let's write the multiplication out in this way. We've done this vector matrix vector multiplication, and we've done there's a variety of ways we can think of it and write it out. And I'm going to use this one here because it's what I want to show. Okay, so I see that when I multiply a matrix by a vector, I get the linear combinations of the columns. So the solutions to A times X, all of those vectors are the column space. The product, I should say, not the solutions, the product of A times X for all possible values of X is the column space. Okay, we can also find a basis for the column space in the exact same way that we would find a basis for any other span. The column space is the span of some vectors, so we know that it's a subspace. All we need to do to turn that into a basis is to identify which of the vectors are linearly independent. Okay, so we're going to continue with this example. We've got that I want to identify which of the vectors are linearly independent. So I row reduce this. We've been learning how to use MATLAB. So this is one of those things where you could enter this into MATLAB and row reduce, and it row reduces down like this. It's a whole lot faster than doing it by hand. And what does this tell me? There is a leading one in each column. This tells me that all 3 vectors are linearly independent. Therefore, these the 3 vectors that I have are a basis. Okay, that these 3 vectors are a basis for the column space. Further, because this is a basis and it consists of 3 vectors, I could write that the dimension of the column space of A is 3. Okay, now we may want to ask ourselves, is some given vector in the column space or not? So I could ask that question, going with the same example here, matrix A on this page. So I could ask, is 2, 3, 4 in the column space of A from above? Okay, now in this, if this question was asked to me directly like this for this example, after I have just found out the basis for the column space, and I know that the dimension of the column space is 3, I could just answer yes, right? Because the column space is R3 and this is an R3 vector. So, look for these sort of things, like be thinking about what the problem is asking rather than pulling out the machinery sometimes when you don't need it. So the answer here is actually yes, because the column space is R3. And so any vector in R3 is in the column space. Okay, so let's just say we didn't notice that. Then we would be asking the question, so that's method 1. You might sometimes be able to tell just given what you already know about the column space. Maybe you don't, then the sort of bulletproof, slightly longer method of doing this. The question is this vector in the column space? The question means is 2, 3, 4 equal to C1, 1, 1, 1 plus C2, 2, 1, 0 plus C3, 8, 5 minus 2. Okay. Can vector 2, 3, 4 be made out of a linear combination of the vectors in the column space? Okay. Okay. So now what you have is what we keep that you notice that this just keeps happening. Now where we're here is a system of 3 equations and 3 unknowns. So we're wondering, is this system consistent or is it not consistent? So what you do is what we're always doing, we're putting that into a matrix and we are going to row reduce. If you are super motivated, I would encourage you to do some of this by hand or enter them into MATLAB yourself and practice your row reduction until you're really confident about it. But I've gone ahead and done this in MATLAB and I row reduced and I got this. There it is. This tells me that C1 is equal to 4, C2 is equal to -1, and C3 is equal to 0. That tells me that yes, the given vector is in the column space, and further that 2, 3, 4 is this specific linear combination, 4 times this one minus this one. Okay. So you can figure actually what the linear combination is of the 3 vectors in the basis of the column space that you need, that then what and in what proportions do you need to form this vector here. Okay, it is the case that the dimension of the column space is equal to the rank of the matrix. And we're going to see more about this coming soon. So here we have the situation. Here we have that the dimension in this example of the column space of A is 3. We already figured that out. And then we'll just take a look at this matrix. When we row reduce it, we see that we've got 3 leading zeros, 3 leading ones. There they are. And that's how we determine the rank. So you can see as the rank of the matrix, the rank of A is 3. And these things will always be the same. Okay, so the rank is, of course, the number of leading ones in the row reduced version of A. Okay. Now we talked about the null space or kernel of a linear transformation. This just can be ported directly over to the null space of a matrix, because we know that we can represent linear transformations as a matrix, and that the determination of the value of the output of a linear transformation can be made by doing matrix vector multiplication. So this is just a porting of the idea of the null of a linear, the kernel of a linear transformation over to the matrix that represents that linear transformation. Okay, so the null space of a matrix is the null space of the linear transformation, or we can say it this way: the null space of A is all of the vectors in the input such that AX, the output, is equal to 0. You'll note that another way we've been looking at this is that it's the solution space of the homogeneous equation. This is the homogeneous equation because that is the 0 vector. So we're just going to do a second example about this. Here we've got a linear transformation, and it is represented by this matrix here. You could, if you liked, try to write out what linear transformation is that L of x1, x2, x3. What does that look like? Right? You should be able to do that simply by multiplying this matrix by x1, x2, x3. Okay, so now I'm going to ask, what is the null space of this matrix? And the null space of this matrix is the solution to the homogeneous, as if this were a system of 3 homogeneous linear equations. So I simply go ahead and I do my row reduction again, and I get this here. Lots of opportunity for you to practice your row reduction procedures. Make sure that you can do this. Okay, there it is. I row reduce, and I'm here. I've got my 2 leading ones, and then I have here a an observation that x3 is a free variable. And now I can write out the solution to this, and that is the null space. So here we go. X3 is a free variable. X2 is equal to x3, which is then also t. And x1 is equal to minus 2x3, which is minus 2t. Okay, so then the null of A is the set containing all vectors of the form t times minus 2, 1, 1, such that t is some real number. Okay, the dimension of the null of A is 1. There's one vector in the null space. So the dimension is going to be 1. I mean, clearly this is also a basis. There's one vector, so it's linearly independent. So that is also a basis. Okay, so we have a basis, and then with one in it and with one vector in it, the dimension is 1. Okay, so notice something here. We had here in this example, we had one free variable, and then that was that the dimension of the null space is 1. Okay, we have that, and then we had because we had one free variable, we had two leading ones. Okay, because we have n columns. Okay, and then we are saying here that the dimension of the null space is the number of free variables. Okay, now if we had right here, we observed that there's one vector in there, it's linear and independent, we got a basis. Now imagine, what if we had two free variables when we found the null space, and finding the null space? Okay, would the dimension, are we sure that those vectors are linearly independent? What if we had two free variables? Our null space would have two vectors in it, one for each free variable. And we would then think, is it a dimension 2? Like, are we sure that they're linearly independent? And okay, so are we sure? And the answer is yes. Okay, when you find the null space of A and you end up with your two or three or four, or how many ever vectors, those vectors are linearly independent, right? You should be sure about that. Okay, so therefore the dimension of the null space is the number of columns of the matrix less the rank. Okay, in this case, we have 3 columns. This is the matrix A, that is n is equal to 3. The rank of A was 2, and the dimension of the null of A was 1, and 1 plus 2 is 3. Okay, so we have that the dimension of the null space of A is n minus the rank of A. Now, this is of course not a proof by any stretch. It is true in general, and we will state it as a theorem within minutes. Okay, but it of course, when it's something as a theorem, it applies to each individual example. So just showing you in this example that this relationship holds. Okay, just before we take a more careful look at that, we're going to just get a handle on the row space. Okay, the row space is the space spanned by the rows. So also we're going to see here that there's an important role for the transpose. The row space is the column space of the transpose. That's how they're linked. Okay, so the row space is the span of all of the rows, which is A transpose X, the same definition like we would have had of the column space, but now of course this is A transpose. So I'm saying that the row space of A is the column space of A transpose. This should just totally make sense. So the row space, this statement here is telling you the row space is the all linear combinations of the rows, and that we can calculate that by calculating the column space of the transpose. So here we've got A is equal to 1, 2, 3, as an example, 4, 5, 6. There's A. The row space of A is equal to the span of 1, 2, 3. That's the first row, and 4, 5, 6. Okay, which is all linear combinations of those vectors. Let's take that away, actually. And T1 and T2 are both real numbers. Okay, so that's what the row space is. Now let's just write out what is A transpose. We take the first row and we make that the first column. We take the second row and we make that the second column. So now we have the transpose. So now let me just look at what the column space of that is. The column space of A transpose. That is the span of the column vectors. Okay, that's exactly, these are the same. So I'm done. This is a specific example, but you can see in general why this has to be true. Okay, the dimension of the row space is the rank of the matrix. Okay, so that's stated here. The dimension of this row space is the rank of A. It's equal to the number of linearly independent rows, and those are the rows whose row reduced echelon form have a leading one. Okay, let's take a look. Let's take an example. We take this matrix here, 2, 1, 3, 2, minus 2, 6, 4, 3, 5. We row reduce, and 1, 0, 2, 0, 1, minus 1, 0, 0, 0. And we note the two leading ones here. This matrix has a rank of, let's call it A. Rank of A is equal to 2. Okay, and the dimension then of the row space of A is 2. The basis for row of A is equal to these two rows here, this guy and this guy. 1, 1, 0, 2, 0, 1, minus 1. Okay, the all linear combinations of those two vectors form are the basis for the row space. Okay, the basis for the column space of A. Now you notice here I chose these two rows in the row reduced echelon form. Okay, and now I'm going to put down what the basis vectors are for the column space. And what I am doing is I am looking here again at the leading ones, and I'm identifying this column and this column as being the columns I care about, but I am not putting these numbers in as the basis of the column space. I am putting in the equivalent columns from the original matrix. Please note this difference. Okay, and think about why it has to be this way. So this is the basis for the column space. So once I've row reduced the matrix, I can get the basis for the row space and the basis for the column space, but I need a little bit of caution. So note the difference here, and then think about this. It is a consequence of the way that the row operations work. The row operations, I mean, for example, we could change the order of the rows. So how can we refer back to this? So think about the way that row operations work and what they do to the rows and what they do to the columns. And that is why this difference is here. Clarify that for yourself, okay? Okay, we have another space that would be the null space of the transpose. And in our textbook, this is called the left null space. I tend to call it just the null space of the transpose, but it is all the vectors for which the solution A transpose X equals 0. It's exactly the same thing, except that we're working with the transposed matrix rather than the original one. So let us just take an example here, A being 1, 2, 3, 4, 5, 6, and then A transpose being 1, 2, 3, 4, 5, 6, like that. And I'm thinking of A transpose X equals 0. Okay, because I'm trying to find the null space of the transpose of the matrix. And so I do the usual sort of thing. I make the augmented matrix. There it is. And I row reduce. There it is. Okay, and I get that X1 has to be 0, X2 has to be 0, and X3 is free. And so in this case, the null space of the transpose is the span of the vector 0, 0, 1. Okay. So there's 4 of these guys. We've now done all 4 of them. There is the column space, linear combinations of all the columns. There is all linear combinations of the columns. There is the null space, the solution to AX, all possible vectors whose solution is AX equals 0. There's the row space, all linear combinations of the rows, and then there's the null space of the transpose, all the vectors X where A transpose X is 0. So let's do a big example where we will find all of the 4 fundamental spaces of a matrix. You got to, this is a useful way. Sometimes we have a matrix and we can, if we find out what these 4 things are, then we can answer questions, whatever the context of our problem is. The answers to these four things will tell us stuff about the problems that we're trying to solve. Okay. Here's a matrix. Okay, I'm just going to make note of what the transpose is. I'm taking row 1 and making that into column 1, row 2 make that into column 2, and then row 3 into column 3. I'm noting that n is equal to 3 and m is equal to 3. It's a 3 by 3 matrix. I row reduce A. So I'm row reducing this guy right above here. I row reduce that, I get this. I get the identity matrix. So the rank of A is 3. It's what we would call a full rank matrix. Full rank, which means that the rank is equal to n. Okay, it's the maximum that it could be. Okay, so that means we can now answer a whole bunch of stuff. First of all, the basis for null of A is simply the empty set. Okay, there's one vector in the null space, 0, the 0 vector. The basis for the row space that is going to be these guys here, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, that's the basis for the row space. The basis for the column space, the basis for the column space is going to be all 3 columns, but we are going to use the columns from the original matrix, 3, 1, 1, minus 1, 2, 3, 6, 5, 3. Okay, there's the basis for the column space. The transpose of A, I will row reduce it. So now I am row reducing this matrix here, the transpose. I row reduce that. It also is row reduced to the identity. Okay, so that tells me then that the basis for the null of A transpose is also the empty set. Only the zero vector is in there. Okay, so let's just see the relationship between the dimensions of these different spaces. We've got 4 fundamental subspaces, and there's an important relationship between the dimensions of those spaces. And it is this thing here called the Rank-Nullity theorem. Okay, we have a m by n matrix. So there is the number of columns. That is the number of columns. And it is the case always that the rank of A, this is why it's called the Rank-Nullity theorem, the rank of A plus the dimension of the null space, the dimension of the null space. These are dimensions. This is a statement about dimensions, not about the actual spaces, but about the dimension of the space. Nullity, we use this word nullity. Nullity means dimension, the dimension of the null space. And that is equal to the number of columns. Okay, so here we're going to take an example of this and see the Rank-Nullity theorem as an example. It looks like this. Take a larger matrix. There it is. Okay, I row reduce using MATLAB. Okay, 1, 2, 0, 3, 0. You can, you can put those zeros in if you want as your row reducing. Doesn't matter because they're going to all be zeros. Just to be clear, what I did here, I actually row reduced the augmented matrix. Okay, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. There it is. Okay, I've got 2 free variables, free variable in column 2 and a free variable here, free and free. Okay, I'll just circle the leading ones to try to make that extra clear. There's a leading one here in column 1, in column 3, and in column 5. There's 2 free variables. There's 3 leading variables. So the first thing, I'm just going to write out some things I can immediately see, that the rank of A is 3. That's the number of leading ones. So that's the rank of A is 3. And then I've got 2 free variables. And I'll just write here what the null of A is. The null of A is the span of, well, maybe I can't do that directly out of my head, or maybe I can, but I would do it in the normal way. Here, this would be x4 is free. It's this guy here. So I'm going to say x4 is equal to t. And I've also got that x2 is a free variable. So I'm going to make that equal to s. And then I'll start looking at these rows, and right here, I'll see that x5 has got to be equal to 0. Well, x4 is free. X3 has got to be equal to minus 4t, because that is x4. And x1 is equal to minus 3t minus 2s. Okay, if you can't do this quickly, like taking this row reduced form of the matrix and getting the solution set out quickly in terms of the free variables, stop the video, back the video up even, and take the matrix, take the row reduced form, make sure that you can write out what the null space of A is. And it is the span of S times, and I'm merely collecting this information up in the normal manner, minus 2, 1, 0, 0, 0, and I've got t here, minus 3, 0, minus 4, 1, 0. Okay, so you can see here that the dimension of the null space is 2. Dimension of the null of A is equal to 2. Okay, and this is then we've got that n is equal to what is n? The number of columns. So let us get a statement of that. In this example, n is equal to 5. There's 5 columns. So I can see that 3 plus 2 is equal to 5. Okay, the rank of A plus the dimension of the null space is equal to the number of columns. That's an example of the rank-nullity theorem. Okay, so there's this is in your textbook too. Very similar statement to this is in the textbook. So what your textbook calling this the fundamental theorem of linear algebra. Okay, so make sure that you can read through each one of these statements and understand what it's telling you. Okay, so it's telling you a few things that we haven't covered. One is we've got a statement what we have covered, what the null of A is, but notice that we can also think of it this way. The null space of A is the vectors, are the vectors n, all the vectors n, whose dot product which each one of the rows is 0. That's just another way of saying AX equals 0. Okay, so phrased slightly differently. And then here you can see that the same thing. In fact, if you want to think about it in terms of a dot product, applies here on the null space of the transpose with the columns instead of the rows. So write out a matrix and write out what AX equals 0 and A transpose X equals 0 looks like, what the linear combinations are, and convince yourself you can see it in this method of using the dot product to state it. Okay. And then we have 2 additional statements here that if we have a basis with k vectors for the row of A, and then we have a basis for the null of A, then the 2 of them together, all of those vectors together, concatenated together, is a basis for Rn. Okay, and that's a similar thing happens for the a basis for Rm. If we take if there's k vectors being the basis for the column, and then another m minus k vectors being a basis for the null of A transpose, then all of those vectors together are forming a basis for Rm. What I'm suggesting you do is do these as an exercise, right? What you should do is get yourself a matrix. Okay, just take some matrix. You can use the one in the above example. Okay, you can row reduce it in MATLAB. And so take a matrix, row reduce, identify the spaces, and then go through each one of these statements, do each statement. Okay? Go through each statement and say, okay, what is this statement telling me? Let me take my example and perform the operations in each one of these statements, and then check that in this example, these statements which are true in general are true for my example, and I see what I'm being told. Okay, that is it. The 4 fundamental spaces of a matrix. Thanks, guys.